All right, good morning. So this morning we're going to go over some rational functions and how this is a topic that there's a lot of parts. There's a lot of moving parts to this, and the more you do these, the better off you're going to. So I'm going to go ahead and share my screen. We're sharing screens. Go ahead and start looking at how to graph a rational function. Now, you don't have to do these steps in the same order that I do. Where you find a rational exponent, horizontal asymptote or vertical asymptote first, it doesn't matter. So here's what you want to do. Your first step here is you want to check for common factors. Okay, now we'll understand when we start doing this. It's a little confusing, but I want to something like, if you tell somebody who's cooking, right? Your grandma cooked, say, hey, you're going to need 6/8 cups of vegetable. She is not going to be happy with you. Okay? Because what do we usually do here? We say that's 2 times 3, and that's 2 times 4, and then we say that's 3/4. So if you tell somebody, hey, I'm going to need 3/4 of the cup, something, then that's a thing they can do. Tell them I need 6/8 of the cup. Like, unless their cup specifically only measures out to 8ths, you're not helping. Okay. The 2 here is a common factor. We cancel. That's all common factor means. Did you cancel something? Yes. So one thing we could do here is do a real easy one. What is the obvious thing to do? Right? The obvious thing to do is to say, oh, well, x minus 2, x plus 2, and we're going to cancel x minus 2's, right? And we're going to have our x plus 2. Now, something that you did learn in 1.8 is that you have to pay attention to domains. So you have to go back to the original function, right? Ever watched A Christmas Carol with Scrooge, right? The first ghost he meets has to drag around those chests of gold that he made in his life for eternity. So when you've done this problem, you have to carry around this x. What if x were 2 here? This function, what if x were 2? It's not going to work out well, right? We're going to end up with a 0 over 0. It's not going to be fair. So you have to exclude that x could be 2, okay? Because of this thing right here. Okay, it's the chest of gold you get to carry around. Even after this function goes away, after it's died, you still have to carry it around. Okay, so don't forget to go back to the original function when evaluating stuff, because this can't happen. Okay. The other thing about this is if x is getting close to 2, what are we left with x plus 2? So we're really thinking about x plus 2, but x can't be 2. Just like you may have started off with, maybe you were doubling a recipe or something, never happened. Like, you might have started the original recipe off at 6/8, but you're going to pretend like it's 3/4, and that's how. So you may have started off with this horrible function here, but after we've canceled, like, oh, that's not bad. X equals x plus 2. That's a line. I got this. It is, but it's not quite there. Domain is a little different than just the line y equals x plus 2. These are very similar functions, right? This means x can be any number. This means x can be any number except for this one. Okay. If you're writing this in set theory, or rather, this is negative infinity up to 2, union with 2 to infinity. Okay. If this is interval, this is what your calculus teacher will be interested in seeing. If you get a little bit further along, you can write down x is an element of the real numbers, except for it's a set difference. It's like minus 2. Okay, that's the set containing 2. It's supposed to be one of these bracket things, but I'm terrible at writing, so. But interval notation is what your teachers will be interested in. If you're writing this by hand, I have no problem writing it either way. I like this because it's a little bit shorter. So what happens here is we end up getting a hole. So we could look at this function, and as x gets close to 2, so we're going to write that as x approaches 2. Okay. When I say approaches 2, I mean gets 2 this way, gets 2 this way. If this plugged in 2 here, what we'd end up with y is equal. Okay. So what if we do like 1.9, and we'll say 2.01, 2. Right? What would my y value be? Well, here it would be 3. Here's my x value. Here's my y. Here it would be 3.9. Here it would be 4.01. Here it would be 4. So we're getting closer and closer and closer into 4 here, but we have to realize like this is not. This is an off limits number. We can't have 2 here. So it's not an asymptote, right? It's getting closer and closer to some specific number. So what we have here instead is we have a hole. So if I were to graph this, right? 2, so 2, that's my intercept. 1, 2, 3, 4. If I didn't have this, we would have a hole. So like this, and then my other intercept, right, is going to be an x equals -2 over here. So we're going to pretend that this is straight. And that's what this graph would look like. So the first step we have is check for common factors. Your book doesn't like to give you a lot of these and tended to move away from them a bit in this class. So it's not a usual thing. It's not common that you're going to have this particular step you have to do. But you should try to find some, if there are some in the homework, because it is for a lot of students, this is a stumbling block. I understand it's a little bit hard to do. So if you can cancel, it's not an asymptote, it's a hole. They can have an asymptote and a hole. That's okay. But if you cancel, the place where you canceled, that is a hole, not an asymptote. Not going to have both of them in the same spot. That's all we do, is just go around it. Always think of this if you're walking along, find Albuquerque, we're not so bad. Clifton Glen doesn't have like pick up your dog waste bowls. So people would just like let that happen. So you're walking along, you'd have to like, whoops, and you barely miss it with your shoes. So you're going around the spot you really shouldn't step in, and that's how I think about it. So that's our step one. But if you don't have it, you don't have this. You can just ignore it and move on. So if my function looks something like this, one with x squared minus 9, okay, there's no common factors, right? If I want to go ahead and so b of x is equal to 1 minus 3, x plus 3, there's no holes, right? There's nothing I can cancel. There's 2 asymptotes because there's 2 spots on the bottom I have to. So the second thing is that we're going to have an asymptote. What you're going to do here is you're going to set, after you factored, check for your common factors. You're going to set your denominator equal to 0 and then solve. So in this case, right, we're just going to say, well, x squared minus 9 equals 0. That's setting the denominator equals 0. X squared equals 9. X squared root principle, right? X is equal to plus or minus 3. So we have two vertical asymptotes. On the line x equals plus or minus 3. Remember, when x equals something, that's a vertical line. When y equals something, there's no x's, that's a horizontal line. If you wanted to solve it this way, that's fine. Okay, either way will work just fine. Whatever you're comfortable with is the way I want you to solve this. Okay? As long as you're getting it right, I don't have a problem. So that's how we find our vertical asymptotes. The way you're going to do this, we're just going to dot them in. 2, 3, 2, 3. Remember, this is x, this is y. So we're on Cartesian coordinate plane here. Right? X equals -3. X equals +3. Does a graph have, does a rational function, does it have to have vertical asymptote? No. So what if we had something like x over squared plus 1? Look at this and you say, set x squared plus 1 is equal to 0. And I know you could say something like this, x squared equals -1, x squared equals +1. But remember what the goal is. The goal is we're going to graph this on an x and a y plane. Now, later on when we get the trig, we're going to be graphing this on the complex plane, which we have a plane that here's my real values, here's my imaginary values. But we're not graphing it on complex plane. We're graphing it on xy plane. Do I have an eye xy? No. So this does not have a solution in the arena, in the universe in which I wish to graph this. So this would be no solution. Real solution. Okay. Again, we will get to this, but now we're not graphing this function xy plane. We're not graphing imaginary numbers on my Cartesian coordinate system. It said there's a complex coordinate system. It looks just like this, but we're not there yet. So in this case, we have no solution, no real solution, so we have no. Now, I'm sorry, this is what's going to make the whole thing. Yeah, this is what's going to make the video a little bit on the side. So here we go with that. Horizontal asymptotes. Okay. Now, vertical asymptotes are sacrosanct. You may not cross a vertical asymptote. We have removed the value from the domain. It's not there. But the range doesn't really work that way. Okay, so the horizontal asymptotes are not exactly, you can touch a horizontal asymptote. Yeah, that could happen. Later on for the electronics, maybe an electrical engineer, you're going to have functions that are going to. And what's happening here, right? It's a signal that's losing strength over time. That's what this is modeled. It happens in other places. But say that y equals 0, right, is a horizontal asymptote. And it crosses here, 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 here. It crosses a lot, doesn't it? Right? It only crosses an infinite number of times. So as long as we can keep it under that, we'll be okay. Right? So can you touch a horizontal asymptote? Yeah. Can you touch a vertical asymptote? Never. So horizontal asymptotes, they're rules, but they're like guideline rules. Honestly, if you walk into a high school class late, they punish you. But it's like the bell just rang. Yeah, you still get detention. Horizontal asymptotes are like how time works in the real world. You come to class and you're like 2 minutes late, like nobody in college, nobody's going to say anything to you. You come in like 30 minutes late, that's a little different, but I won't say anything to you. This is, if you clock into work 30 minutes late, your boss will have something to say. It's a role. You clock into late class 2 minutes late, boss might have something to say, but quite honestly, if your boss is like, goes in over 2 minutes, you don't know. What do you do? Is this the problem you have? There's other things to worry about. So there's rules, and then there's like guidance. Horizontal asymptotes are like guidance. Vertical asymptotes are absolutes. Okay. So how do I know what kind of vertical asymptote or horizontal asymptote I have? Well, if there's four cases. So here's case one, case A. If the degree, the numerator is less than the degree of the denominator, and we have horizontal asymptote. X y equals 0. So both of the things that I showed you before, right? This x over x squared plus 1, that function, the degree of the denominator, or the degree of the numerator, is 1. The degree is 2. Right? How did I get that? The degree is the exponent, the biggest exponent. So the degree of the numerator is 1 here because of the linear part. And down here, the degree of the denominator is 2. So x squared plus 1. 1 is a smaller number than 2. So our horizontal asymptote is y 0. Actually, I knew this was going to happen. Let me go ahead and graph this one. We'll refer to part 2 in just a moment. So if I was going to graph this function, trying to see it, we have no vertical asymptotes. We have a horizontal asymptote. It's not really above the line. It's the same line as this. It's easier to see. If I set it equal to 0, make it a different color so you can see it. And let's go ahead and graph. Now there's not really a whole lot to do here. So what we're going to do is we're going to make a t-table, right? And we have to pick different x's and y's. Okay. Now, one of the things that we're going to make this a little bit better is that we're going to see if we can be clever. So the problem here is that the issue here is that x over x squared plus 1, this is what they call an odd function. Okay. You may have remembered this from college algebra. You may have remembered hearing about it. So when am I ever going to use this? So what an odd function is that f of negative x equals negative f of x, then the function is odd. Okay, this means it's symmetric about the edge. What happens up here is going to happen. So quadrant 1, right, is going to be similar to quadrant 3, and quadrant 2 is going to be similar to quadrant 4. So whatever happens in quadrant 1 happens in quadrant 3, whatever happens in quadrant 2 happens in quadrant 4. So they're diagonal to each other. So what we're going to do is we're going to replace. We're going to say, well, f of negative x, okay, is equal to negative squared plus 1, and we end up with over x squared plus 1, which is negative x over squared plus 1. What do we start with? X over x squared plus 1. What do we end with? Negative x over x squared plus 1. So this is the case that we have. A function is even if f of negative x is equal to f of x. Okay? So we do the same test and we'd see what we end up with. Okay? 1 over negative x squared minus 9, right, is 1 over x squared minus 9. Remember our first example, right, is this one. They're the same. So this is an even function. So again, like this is symmetrical at the y-axis. So what happens here is going to happen here. What happens over here is going to happen. So let's go ahead and take a look. So x equals 0, y equals 0, x equals 1. So we have 1 over 1 squared plus 1, which is 1/2. Okay. 0.5 when I go to graph. Negative 1, you have negative 1 over squared plus 1. And so that's negative 1/2. So f of 1 was 0.5. F of negative 1 is negative. Got 2 and negative 2. We have 2 over 2 squared plus 1. So that's 2 over 4 plus 1 is 5. What about negative 2? Negative 2 over 2 squared plus 1. So we have negative 2. So f of 2, right, is 2/5. F of negative 2 is negative 2/5. So we're doing 1 more. 3 and negative 3. So this is going to be 3 over 3 squared plus 1. So that's going to be 3 over 10. Oh, wait, 2/5 is 0.4, negative 3. What are you going to guess? Right? F of 3 is 0.3. What is f of negative 3? That's the idea of being odd. So if you know something is odd, I really don't graph. I only need to calculate 1, 2, and 3, and then I could just know what negative x were. So we'll call this will be 0.5, 4.3, 2. So we have one here, 1 here, 2 and there. You could keep going out from this thing, but it doesn't just go down like a line does. It's close to this asymptote. It does something like that. And then down here, it's the same thing. So in the end behavior, you want to hug your asymptote. Closer and closer and closer to it. We could test whether or not it gets crosses. It does not. So it does here. That's it. I'll show you how to do that in another video, but now this is long enough. So we're going to cover case 2, 3, and 4 in the next video, and then we're going to do some examples. Okay. So I'm going to stop us here and say, just a moment.